Okay, I don't want to go deep detail into this discussion, because this one just want to prove how actually, where actually this least square method come from. Actually, it's come from the to, in order for you to obtain, again, in order for you to obtain the best fits linear equation or linear regression that fits with your data, of course you need to find the minimum value of your j. Of course, of course this one is a plot value of so once you plot like something like this, it's actually in the real world it's very difficult for you to plot something like this. And then once you plot, it's of course the minimum is at that point. Okay, if you remember that that in order to generate the whole thing, all possible of b0 and b1 that producing your cost function, I can consider it as some kind of impossible mechanism, because there's a lot of b0 and b1 need to be generated, so you can produce huge number of cost value before you can produce something like this. So that is one way that kind of approach. It's impractical because that is required more time to find the optimum value. However, okay, so before we go further into this thing, actually this is what we call as when you do iteratively to find to find the best b0 and b1 that is minimize your cost function. That is what we call as a hyperparameter tuning. Okay, I think you remember about the previous lectures. You also exposed to the term called hyperparameter tuning or optimization, and how actually we can do this one, meaning that how can we optimize our b0 and b1. Of course, you have learned so far that what we have learned so far is what we call as a least square method. So what is least square method? Actually, it's originally come from here. So again, this is what we want. Okay, this is our objective. We want to find our beta there. Okay, sorry, it's not b, beta. So just put head there because it's a predicted beta. Okay, why the mathematician put the head there? Because the actual beta, of course, we cannot get, because we just imagine, but we cannot get the actual minimum value. Sometimes we just close to the minimum. We can get some beta which is close to the one that can produce the minimum value, the optimized one. So that's why they put there as a hit there. Okay, just a predicted or something which is close. So that's why they use the notation as a beta hit there. Okay, now we want to find the objective. This is the hyperparameter tuning approach. Okay, this is what we call the hyperparameter tuning, because we want to find the optimized optimized beta that can produce the j with the minimum value. Okay, this is how we express the equation. So again, this is a least square method is come from the very fundamental things that you learned before. If you remember when you learned in your secondary school, okay, if let's say this is your beta, okay, I don't draw in this way. Okay, I will draw it in 1D. Okay, assume this is my beta. I put it bold beta because it represent our b0 and b1, and then this is my j function or my cost function, which is my b1 and b0. Okay, so let's say this is the one dimensional, a cross section of this one. Okay, you can imagine whether the cross section in this way or in this way. Okay, just imagine I plot back this thing. So it will look like something like this. Okay, so again, if this is the function and you want to find the minimum value, if you remember what you learned in secondary school, in order for you to find your beta here, which produce the minimum value of your j here, one way to do that is through what we call as a derivative operation. Okay, that's why you learn in your secondary school, which is called as a derivative. Okay, so from here That's why you can see here, if you want to get the minimum value, to minimize your j function, we can set our derivative and make sure your dj db is equal to 0 in order for you to find the optimum b, or the optimum b beta there, not b, sorry, I always say b, should be beta. Okay, so that is how it's work. But however, this one right now is not just some scale value, it's a vector. That's why there's a bold there. So that's why, because this b is actually represent multiple b0 b1 until bd. Okay, that's why you cannot use a derivative, but you are using a partial derivative, which is represented by this one. So that's how we proceed with finding the minimum value, the minimum cost function, and from there you know what are the parameter which is your beta represent, that can produce the optimum beta that can produce your minimum value of your cost function. Okay, so I don't want to highlight on this one, you just can see over here is the partial derivative between the matrix or the vectors. Okay, this one is come from the previous slide, which is this one. Okay, this one. Okay, your cost function is a sum of square error, SSE, remember. So you need to derive the sum of square error here, do a partial derivative. So you can see here, this is where this is where you can see the reason why we put 1/2. Okay, why we put 1/2 at the end? Because if you remember, this one is, if the element inside here is a square, there's something a square here. So if you put a derivative, then these two going into, if you derive this equation, these two going to add here, okay, at this one, and if you this one multiply with 1/2 multiply with 1/2, you will cancel each other. Okay, so that's the reason why we put 1/2 there, okay, from the previous lectures, because because at this stage we want to do some partial derivative with your sum of square error. So if you have 1/2 at the beginning, then you can cancel with the square that bring down as a multiply by 2 of the partial derivative. Okay, so that's why at the end you can see that 1/2 have been disappear here. Okay, because of the 2 here is going to that. But the one that I want to highlight is that this is what we call as a least square method that you learned before. So at the end, the general equation for least square method, okay, another name for least square method is also known as a normal equation, or is also known as a closed form of your cost function. Okay, if you search into many source, some people will always highlight this term, closed form normal equation. Actually that is referred to your least square method. So at the end, okay, this is the general equation, but now let's go to the example here. Let's say you are producing the least square error here, the same operation, the same as this one, but you are proceed with one input variables. Okay, so you means that your beta here consists only with beta naught and beta 1. So again, we want to minimize this one, and this is the equation which is come from here. Okay, after you do some derivative here, partial derivative, and then if you extend, this is how you see the definition as before. This is your x, this is y, this is your matrix x, or we call as well as a design matrix, and this is your parameter. Okay, consists only b0 and b1. That's why you only have one x1, one x2, meaning that you only have this one is actually one input. Okay, you have only one input. That's why you only have x1, x2. This one input but more data. So that's why let's say you have 1000 data. So meaning that you have, if you have x and y, this is a y, this is your x. So this is the value. Okay, this one going towards 1000. Okay, meaning that this one represent this one will represent this one, but you need to form as a design matrix where you put 1 at the first. This one because of, again, we already discussed, this one is for to proceed with the B naught. Okay, B naught is a intercept, y intercept. Okay, so that's why you put 1 there. So from here, then actually from here you can see that from the normal equation, okay, this is your normal equation. If you see the normal equation is this one. Okay, this is your normal equation, but I don't want to discuss more about this one. I just want to highlight that this one you can change in form of this one. Okay, you can find out by yourself actually this one, okay, by having this x. Okay, if you try to see this x, you can extend this one by having this information. You can change your normal equation here as this one, and later once you do all the things here, actually lastly you find out that the solution there, your beta 1 is this one, and your beta naught is this one. Okay, if you see over here, this is actually again because this is a one variable example, of course this can be your C, this is can be your M. Okay, y equal mx plus c. Remember that this one is beta z naught, this one is beta 1, one variable example. So that's why this is your C, this is your M. So if you see this operation, actually is similar to what you learned before here, this one. Okay, so you try to compare this equation, this expression, and this expression. Actually is similar. Okay, so that's why this one just want to prove that actually this is just one variable example. If you talk about multiple input or multiple variables, then that doesn't matter is it one variable or two variable or multiple variables, then this is actually the one that represent the solutions, okay, for all of this. Okay, so in other words, why you learned why least square method have this kind of equation. Okay, how come this operation, the mathematician produce this expression, actually is through this concept. Okay, because you are actually the history behind it, actually you are measuring the cost function. Once you measure the cost function, and you are using the cost function which is called sum of square error, and then the objective right now, in order to find the best fit linear regression model that fit with your data, of course you want to make sure the total error or the cost function here is minimized. Okay, the best is must close to 0. So one way to do is through doing a partial derivative of that cost function. That is what we have done here. And then at the end, if you talk about the one variable examples, this is how it look like, which is similar to the previous course that you have learned before, in order for you to learn how to find the best model that fit with your data. However, you can see that this one, I just want to prove to you that that is one of the mechanism. Okay, least square method is one of the mechanism to find the best fit linear regression model that fit with your data. And actually the basic of this thing is by doing the derivative of your cost function, and in this case the cost function is sum of square error. Okay, or in other words, you are square the error, and you total up the total error to find the total error, and you want to make sure that error is as minimum as possible if you vary your B0 and B1, or if you are vary your you vary your beta naught and beta 1, or you vary your beta. Okay, so I hope you you understand about the concept of this one, because this one is just some additional information, so you might the concept is there, but I will, of course I will not ask you to derive all these things, just give you some exposed to what happened, so later you are prepared yourself in order for you to understand the more complicated things such as artificial neural network.